a new topic, which is DC motor. طبعا يعني all of you are familiar with DC motors. However, we will cover يعني something different to what you have already learned before. We will start today with the DC motor dynamic analysis. So the objectives of today's class, شباب, we'll discuss the separately excited DC motor dynamics. We'll drive a block diagram for a separately excited DC motor. That's what we need to implement on any simulator in order to simulate or control this kind of motor, or even not only simulator, we can implement this on any digital controller like Arduino, like FPGA, like digital computers, microcomputers like Raspberry Pi, like BeagleBone. All of these digital controllers we can apply in order to control the DC motor. So this block diagram is very important to be understood and implemented on these controllers in order to control the DC motor. Also, we will discuss the speed response of separately excited DC motor with a step change in the applied voltage. So this is the objective of the today class, inshallah. Firstly, let me discuss with you what is the problem of dynamic modeling and why we need modeling for electrical machines. First, شباب, you know that if you have inductance in motor, and this inductance, there is a distance between these two inductances, and this distance may be variable distance, may be changed, maybe the geometry of the machine changes, where you have motor windings on the stator side and rotor side. So if there is a mutual inductance between them, and this mutual inductance will be variable value, it will not be fixed value. Why? Because the distance between the values will be changed, and also the angles of these or the geometry of the angles will be changed as well. So for that, the value of the inductance will not be constant all of time. It will be variable inductance during the operation and during the motor rotation and even with loadings. So in order to make a simple model, this is not easy. However, we can make this by dynamic modeling and include all of parameters. We can use some simplifications. However, the accurate model will give you the most probably response close to the reality. So it's better to include everything in your model. For instance, شباب, if we describe the induction motor, here we have an example for a modeling of induction motor. For instance, if we started analyzing the induction motor, you will find that induction motor 3 phases. So we have A, B, C phases, and you have stator and rotor. So it's not easy to make 6 parameters or 6 equations for each phase in stator and rotor. So instead of doing that, we make something else called DQ model. There is another type of modeling, شباب. Instead of making 3-phase models, there is another model called DQ0 model, or arbitrary reference frame. There is a theory in electrical machines called reference frame theory. Reference frame theory, simply, it's making a model for any machine and considering a certain frame for the operation. For instance, we discussed previously that in induction motor we have 2 objects. We have stator and rotor. And if you are standing in the stator side, you will see the flux is moving by synchronous speed, and you will see the motor rotating by the value of NR or rotor speed. However, if you stand on the rotating flux, and assume that the rotating flux is an object and you will stand on this object, so your speed will be the same as synchronous speed. In this case, you will see the parameters of rotor circuit moving in a speed equals ns minus nr. And you will see the stator parameters, which were constant. You can see it now moving with speed ns. So this is called now reference frame. According to the frame that I will stand on that frame, I can see all of other parameters moving in different speeds. For that, شباب, we made, using reference frame theory, we made two different or three different frames. We have something called synchronous reference frame. We have something called rotor reference frame. And we have something called the stationary reference frame. Stationary reference frame, you will see everything variable. If you are standing in synchronous reference frame, all what you can see moving in the value of synchronous speed will be almost as DC, because it's constant now. So what will be the added value now? If you stand at the rotating object of the synchronous speed, which we call it a synchronous reference frame, in this case, any variable as a function of synchronous speed will appear as DC. So this will be easier in calculations, شباب. Can you imagine that, شباب, or it's not clear? Please,
It's
discuss.
clear for me.
Can you repeat it? Can you repeat it?
Again, I will repeat it again for you. Just let me give you an example from our life. If you are standing at the bus station, okay, at the bus stop, and you can see the bus is moving, okay, with a certain speed, you can see all of people inside this bus are moving with the same speed. Is it right?
Yes.
Right. If the bus is moving in variable speed and you need to make a mathematical equation for these movements, is it going to be easy for you to do that? Well, you are stopping at the bus stop. It will not be easy, because you will see the bus is moving in different speeds, and if you would like to make an equation for that, it will not be that easy. صح ولا غلط يا شباب? However, if you are standing inside the bus itself, you will see all of people inside the bus are not moving. They are stay inside the bus, and the bus is moving with the speed, and they are moving with the speed of the bus itself. So if you are inside the bus, you can see everything is fixed. مظبوط ولا لا? Is it clear? For that, if you make the same for machines, for induction motor, for instance, we have the parameters of stator, which are a function of the frequency F1. All of these parameters are moving or a function of frequency F1 on the stationary reference frame. However, if you stay on the synchronous reference frame, which means you are going to rotate with the synchronous speed, you will see all of the parameters as a function of frequency F1. You can see all of these variables as constant. Is it clear, شباب?
The concept
Yes,
for me is clear, but how can we implement it in our examples?
How can we implement? We have to make mathematical derivations for all of the equations. Okay, but the theory itself or the concept, is the concept clear? if we have a voltage, if we have a voltage moving with a certain frequency, 50 or 60 hertz, if you are moving with this vector of voltage, you can see this vector as DC supply. Is it right or not?
Yes.
Yes.
So this is now the meaning of reference frame. So if we work with reference frame now, we can simplify our models. For instance, you can see the values of inductance or mutual inductance between stator and rotor are depending on the movement angle, which is depending on the rotor speed. So if you would like to make this variable as constant, start working on the rotor reference frame. you will see the mutual inductance constant all of time. This is an example, يا شباب. For that, يا شباب, we have many models. You can have a model for induction motor or synchronous motor at synchronous reference frame, at rotor reference frame, or stationary reference frame. So there are lots of models of AC machines. This is, for instance, one of the models, يا شباب, using one of the reference frames and using also something called arbitrary reference frame. Arbitrary reference frame, which is called DQ0. This is the arbitrary reference frame. It can be made to be variable as synchronous, rotor, or stationary reference frame, which means we can substitute with the angles. In this kind of frames, يا شباب, if the machine is stable, if the machine is balanced, three-phase system, the zero component will be zero. The zero sequence will be omitted from the model, and you will have only a value for D and Q. So you can convert now a three-phase circuit to only two components, D component and Q component. For that, you will find the induction motor, the balanced three-phase induction motor, has two circuits. One is called D circuit and the other is called Q circuit. Okay, so based on D and Q, we can make a mathematical model for our machine. You can see here VDS, VQS, VDR, VQR, which are D component for stator voltage, Q component for stator voltage, D component for rotor voltage, Q component for rotor voltage. So this now represents the electrical quantities of the induction machine. So we have four equations or a matrix of 4 by 4 that will represent the induction motor in DQ frame as a function of IDS, IQS, IDR, IQR, which are stator and rotor currents in D and DQ frames. So this now representing, يا شباب, the electrical model. Now for any electrical motor, it's not any electrical model. It's not only electrical model. It's electromechanical model because we have something mechanical. We have rotation. So from the dynamic equation, which is T electric minus T load equals J d omega by T plus B omega, and we wrote the equation before and we will discuss it here in details today, inshallah. This equation is called dynamic equation. It represents all of the mechanical motions of electrical machines. From this equation, we can get another equation for the motor which describes the mechanical model. So if you make that, you will find the torque equation for the induction motor equals lambda QR IDR lambda DR IQR. This is the final equation of the derivation. I'm not going to discuss the derivation of induction motor. However, this is the final model of the induction motor. This is just to show with you that modeling of electrical machines is not that simple. We discussed previously the induction motor equivalent circuit and all of the circuits that we could see that we have only R1, R2 prime over S, X equivalent, XM, RC. This is actually a very simple model. It's very approximated. However, if you would like to get the exact model, you have to consider all of these parameters. Okay, شباب? طيب, why we need these models, يا شباب? Why we should use these models? Now we know already the steady state approximated models. For induction motor, previous topic, for induction motor, we discussed all of things regarding induction motor at steady state, and even sometimes some parts of transient, or we go to the dynamics a bit in the part of starting or breaking or like that. However, we did not go in deep in transient operation. So, شباب, in order to analyze the transient performance, in order to analyze in detail model of induction motor, you have to use these types of models, not the equivalent circuit what we have described before. Let me give you also another example. Now we discussed the induction motor. We can make a speed control of induction motor using variable voltage, for instance. We use the variable voltage in order to what, يا شباب?
To control the speed.
Control the speed, exactly. Type, let me now give you an example. I have a motor with a certain speed moving, with a rated speed of, for instance, 1700 RPM, and the synchronous speed is 1800. And this motor, you need to control this motor in an electric vehicle. So in electric vehicle, if the reference speed going to be constant or variable, يا شباب? Reference speed, it means the command of speed that you are going to give it to the motor in order to operate your car. Is it going to be fixed or variable?
Fixed.
So you are going to move with the car in a fixed speed?
No, it should be variable.
It should be variable. تمام? Variable according to what? Variable according to the desired value you are going to apply. You are going to use pedal, for instance, and this pedal, if you press on this pedal, it will give a certain voltage to the machine in order to give a certain speed. So based on a reference value, you are going to apply as a command, you will get the certain speed. So now you don't have a definite speed you need. You have a variable speed or need lots of commands of speed. You cannot make your calculations in order to get which value of voltage should apply now in order to get that speed. You have to make something adaptive. Something adaptive means closed loop control. In order to make closed loop control, you need to add something called controller or compensator, like PI controller, for instance. This controller need to be tuned in order to control the machine speed at the desired values you need. How we can tune these parameters of PI controller? Just by knowing the machine parameters and knowing the machine model. We have some control techniques, need the mathematical model or the mathematical model of the motor in order to make this control, like something called model predictive control, like something called direct torque control. Okay, in these types, Shabab, you need a detailed model of your motor. For that, studying the dynamic model is very important. So, in this chapter, inshallah, we will discuss the dynamic model of DC motor. And by the end of this chapter, we expect from your side, inshallah, to make the complete mathematical model for the DC motor and use a proper power electronic converter in order to control the motor speed, not only in the motoring mode, but also in the regenerative mode or reverse motoring mode or any kind of braking. So we will discuss everything about the dynamics. We will discuss the mathematical model, and you will implement this on MATLAB Simulink. And this will be, inshallah, the topic of your course project. By the end of this chapter, we will make the announce of the course project, and you will understand in details what is needed in your course projects. Okay. By the way, this is considered as one part of the laboratory as well. So if you are taking the laboratory with us, and yesterday we started in the modeling of DC motor for the first group. Today, inshallah, second group will start in this experiment. We will determine the parameters of DC motors which are going to be used in modeling and control and tuning the controller of DC motor. Okay, so this is already a part of the lab. So, with the course and lab together, by the end of this topic, inshallah, you will be familiar with how we can make a mathematical model specifically for DC motor, but in generally, it can be made for any kind of motors. So, as we are going to make for DC motor, you can make it later for induction motor, for synchronous motor, for stepper motor, for whatever the kind of motors you need. Okay, Shabab? So,
do you mean by mathematical model like something like transfer function?
Yes, exactly. The last thing you have to obtain from the mathematical model is the transfer function. This is one of the solutions needing control. Sometimes we need something like state space model. And here, for instance, the equations you have here can be used in a state space model. So you have state space, you have transfer function, and we have many techniques, Shabab, in order to control our machines. According to the control technique we are going to use, you have to specify your needs, your specific shape of model. Okay? In our model, in this chapter, we will consider the PI controller or PID controller. For PID controller, transfer function is important, not state space model. However, if you need model-based techniques like model predictive control, for instance, you have to have a state space model because you need after that to make discretization and a lot of things from state space. So the most easier way we are going to describe in your course here, because this is undergrad level. However, if you continue in postgraduate, inshallah, and working in this kind of fields, in electrical drives and power electronic control of electrical machines, you have to understand how you can make mathematical modeling using state space model, for instance, for the different type of machines. Okay. So start, Shabab, from scratch. All of you are familiar with the equivalent circuit of separately excited DC motor. We have field circuit, we have armature circuit. In the field circuit, we have RF and LF.
Doctor,
Fadal.
you said we will not use steady state space in DC
State
model.
space, yes, state space model. We are not going to use it here because it's based on mathematical calculations using matrices, and this is not easy to be discussed here in classes. However, analysis using transfer function is much easier.
Transfer function, that's what we use.
Yeah. Okay. Yeah, I believe you know already part of this, Shabab, because you studied before or you learned the EE 380 course, which includes parts of what we have discussed today. Okay, but unfortunately yesterday your colleague said to me, you did not learn the PI control or PI controller or PID. Tamam? However, as we can, inshallah, we will cover this in our course and laboratory. So, in order to start with DC motor, Shabab, we start from scratch with the mathematical model of the motor. We have field circuit, which includes R and L. Also, we have armature circuit, which includes R and L. We have supply voltage. We have EMF. We have mechanical parts, which includes shaft, and this shaft will move in a certain speed by electrical torque T, and there will be a load connected with a load torque TL. One can say we have here DC motor. Why we need to discuss the effect of inductance? Can somebody reply to this question, Shabab? Why we need here to study the effect of inductance, since we are going to work with DC, and you know DC at steady state, the voltage across the inductance will be zero.
To see the effect in the transient state.
Exactly. So we need to make a mathematical model to include all of modes, transient and steady state as well. For that, you have to study the effect of inductance as well. So we will take in consideration of our mathematical model the value of inductance here. Firstly, Shabab, the equipment we have armature resistance, armature inductance, field resistance, field inductance, armature current, field current, terminal voltage, field voltage, EMF, which is the induced voltage. We have T, electrical torque, TL, load torque. Other parameters, we will discuss it during the model, inshallah. So for now, you know that the effect of field can be obtained or developed to the armature winding by means of flux. So you know that EMF value equals constant multiplied by flux multiplied by speed. Similarly, torque equals to constant multiplied by flux multiplied by armature current. And we are not going to consider field circuit here in our analysis, but we will take only the her effect or its effect, which is the value of flux. Okay, but the value of R, F, and LF will not be considered in our circuit because here we have separately excited. So we will consider only the effect of field winding, which is the flux value. Now, we need to replace the flux with its main component. You know, flux is a function of the field current. So we can say now phi equals K multiplied IF. So finally, you can say that EMF equals KF multiplied by IF multiplied by omega. T equals also KF multiplied by IF multiplied by IA, where KF here equals K multiplied by KA. So this is now KF. For separately excited DC motor, you don't need to include IF in the circuit. So we can even remove IF with KF and replace them together by another constant, and we can call it as Km. And we can call this Km as motor constant. We can call it as motor constant. So Km is considered as motor constant. Now, we can say also electrical torque equals Km multiplied by Ia. So, two main equations we could obtain by or from the effect of flux, which are EA and T, induced voltage and torque. Induced voltage equals Km multiplied by omega. Torque equals Km multiplied by Ia. By the way, what is Ka, شباب, here? We have constant Ka. Do you know what is Ka? It depends on what? Do you remember that relation يا شباب? PNZ over A. ها؟ فاكرين حاجة زي كده يا شباب؟ It's related to the A winding, صح يا شباب? Winding of the machine. يعني if you review the E360 course, you will find that DC motors have the motor constant, which is depending on number of poles, number of conductors, number of turns, and number of parallel paths. All of these variables are يعني constructing the variable of K. تمام? So it depends on the machine windings type. And the similar equation for that in AC machine we used before, which was, as you remember, E equals 4.44 multiplied by phi Fn K winding, like that. You remember this equation in AC? This is the EMF in AC, and here this is the EMF in DC motor. Okay, so all of parameters here equipped in the variable K type. So finally, we have here two equations now, شباب. Motor constant multiplied by omega and motor constant multiplied by current to represent EMF and torque. Now, let's start with the electrical model. We have electrical model of our machine. يعني طبعا يا شباب, in order to solve the time domain equation, you know, time domain equation, we will end up with differential equations because we have L and R here. Some circuits you may have L, C, and R, so the differential equation will be second order. But here, because we have only R and L, there is no capacitance, so it will be first order differential equation. In order to solve first order differential equation, it's very easy to be solved if we convert from time domain to Laplace or S domain. So we need to convert everything to S domain. So we can say T of S equals Km multiplied by I of S, and EA, EMF as a function of S, equals Km multiplied by omega of S. Now, if we made a Kirchhoff voltage loop for our motor, we can say now V terminal, this is in time domain firstly, V terminal equals EMF plus RAIA plus LA DIA by dt. And simply, you can replace E by K multiplied by omega. If you convert from time domain to S domain, so we can say now Km omega of S plus, here you have RAIA and here LA DIA by dt. You know d by dt in Laplace domain converts to S. So we can say now SL and take I as a common factor. So we can say R plus SL multiplied by IA of S. This is now the Kirchhoff voltage law equation for the DC motor. If you would like to represent the machine, sorry, if you would like to represent the machine parameters in terms of time constant as electrical or mechanical, so we can say electrical time constant tau A equals L over R. So just take R as a common factor, we will find here L over R, which is representing tau. So the relation can be Km omega of S plus R multiplied by 1 plus S tau electrical multiplied by I of S. So this equation now, Shabab, representing the electrical model. Can you now compare between DC and induction? So here you have only one equation, which is considered as a mathematical model for electrical model of DC motor. Can you go back again to the induction? You can see here it's 4 equations after simplification. So here we have 4 equations after converting from ABC to DQ, which means the DC motor model is very simple compared to other machine models. تمام يا شباب? Is it clear? For that we consider this شباب in our course here, because يعني other models are not suitable for undergrad courses. طيب. Now, after obtaining the electrical model, let's start in the mechanical model part. Any mechanical motor يا شباب, we can represent the mechanical motion by something called dynamic equation. Dynamic equation is nothing but T electric minus T load equals J d omega by dt plus B omega plus K theta. Or you can say J d square theta by dt square plus B d theta by dt plus K theta. So you can represent as a function of angular displacement or speed. Okay, we can represent the dynamic equation as a function of angular displacement or speed. For simplification, شباب, we can neglect the part of elasticity K and remove this part from the equation just by neglecting this part. Why we do that? Actually, we do that to simplify the model in order to, instead of making a second order differential equation, it will be only first order. So we can neglect this part of the dynamic equation and consider only the machine is working as a function of omega, which is the angular speed. So we can say now T electric minus TL, which is the load torque, equals J is the moment of inertia of the moving part, which is rotor. J, طبعا J شباب, the moment of inertia is calculated as mr square. M, the mass of the rotating rotor, rotating mass. R is the radius of the rotor core. تمام? So this is representing the moment of inertia of the machine. So J d omega by dt plus B omega, B representing the friction coefficient, or we can say it's a viscous friction coefficient. So B multiplied by omega representing the friction torque. Okay. So if you apply this to our motor here, you will find that T electric equals KMIA, and TL is moved to the other part in positive sign. So the equation is J d omega by dt plus B omega plus TL. Now convert to S domain, so we can say KMI of S equals JS plus B multiplied by omega S plus TL of S. If you would like to make omega in another side, in the left hand side, so you can say T minus TL over JS plus B, and also you can define here the mechanical time constant, similarly as we have made an electrical equation where mechanical time constant equals J over B. So now we could describe our machine by 2 equations, one for electrical and one for mechanical. This is the electrical, and number 3 here was the mechanical. So let's now converting these two equations, شباب, into block diagram in order to start making transfer function and understanding how we can make a block diagram for our motor. So simply, let's start with the electrical part. I equals V minus K multiplied by omega S, which is E of S, over R multiplied by 1 plus S tau A. So how we can represent a block diagram? Simply start with the numerator, شباب. V all of time will be the input of our motor. So this is the input. Here we said V minus something. This part will be a function of omega, and we did not obtain omega yet, so assume that we have here summator, and this part here we don't know coming from where, but assume that it's E now. Okay, so you have plus minus, and the output here will represent the numerator. If you would like to get the current, so you should multiply by 1 over denominator block, which is 1 over R multiplied by 1 plus tau AS. This will give you the value of current. So this part now representing equation number 4, which is the electrical motor. Right. Let's see together equation number 3, which is the mechanical. We said here for the mechanical, T electric, which is equal to Km multiplied by I, minus TL divided by some parameters equal omega. So here we have T electric, which is I multiplied by Km. So this is now T electric. Minus TL. This will give you this quantity, which when we multiply this quantity by 1 over B multiplied by 1 plus tau mechanical S, this will give you the equation of the speed. So this part now represents the mechanical equation. Just to connect between the two equations together, you have the relation that EMF equals K multiplied by omega. So we will multiply as a feedback like that to get the value of E of S here. So this block diagram now, شباب, the input is V, which is the supply voltage. The output is omega, which is the motor speed. So this now can represent a complete block diagram for DC motor. If you would like to get the transfer function of this model, simply you need to get omega of S over V of S. So this will represent the transfer function. طيب, any questions, شباب, up till this part? Huh? Up till this part, everything is clear? Good. You know, شباب, from the simplifications of block diagram, if we have a block diagram like that, the equivalent one will be, and here we have the forward block, which is U of S, back is H of S, output C of S, input R of S. So if you would like to get C of S over R of S, you can represent it in one block like that, which is G over 1 plus GH. Okay, so this is, I think, it's well known for you in previous courses. For our block diagram now, طبعا it's not easy to be made because we have two inputs. If you have a look here, you have one input here and another input there. Mathematically, TL is considered as input, VT is considered also as input. Right? طبعا it's not easy to be simplified from this way here. However, if you would like to get the transfer function, you have to use the mathematical equation 3 and 4 up to reaching to omega over V. Okay, and it's not a big deal. However, it's complex a bit. But for simplification, let's make it here now in order to find a transfer function at simple assumption. So assume firstly we have TL equals 0. So you will have only one input, شباب, which is V. If you would like to get now the transfer function as omega over V, so simply if we return back again to the block diagram, we can say now all of parts here, all of these 3 blocks multiplied together will represent G of S, and Km will represent H of S. So we can now use the relation, this is G of S and this is H of S, and substitute in the relation G over 1 plus GH, you will get the transfer function of this case, which is omega over V at TL equals 0. So this is one case here, Shabab. We can also make another transfer function if we consider the input as TL and the output is omega, and considering Vt of S equals 0. So in this case, let's go again to the block diagram. If we consider that this equals 0, V equals 0, so this means these 3 blocks are considered now as G, or sorry, as H, okay? And this block is considered as G. This is a forward and this is a backward. For that, if you substitute now in this case, we can consider G as 1 over B multiplied by 1 plus S tau mechanical, and H considered as Km square over R A multiplied by 1 plus S tau electrical. So substitute in the equation again, G over 1 plus GH, so you can get the transfer function of omega over TL. So this is now representing this transfer function. So it's up to our needs, Shabab. What is the transfer function we are going to use? If we use the motor, or if we would like to control the motor and get the parameters of transfer function as omega versus V, so you have to use the first one. If you need the second one as a function of TL, so you have to use this one. We have some special cases as well, Shabab, for the same transfer function here. If we have a load which is proportional to speed, which means torque load equals BL multiplied by omega. You know we have some kind of these loads, Shabab. Torque is proportional to omega. We have torque is proportional to omega square. We have torque is proportional to 1 over omega. So a lot of loads are a function of speed. So for instance, assume the most simple one is TL equals B multiplied by omega. If you would like to simplify the mathematical model and get the transfer function of omega over V, we're considering TL as constant load. So for now, you consider, sorry, not constant, torque proportional to speed. So now you consider your torque, but as a function of omega, and you add it in the equation to get a complete transfer function without the assumption of zero load torque. So here, just we need to substitute TL by BL omega. So in the mechanical equation or dynamic equation, we can say now Km multiplied by I, which is T electrical, equals JS omega plus, you know the relation was B omega plus TL. Now TL is B multiplied by omega as well, BL multiplied by omega. So we can say B plus BL multiplied by omega. And now we consider B plus BL as 1B as B total, for instance, and get the same equation. تمام يا شباب? So this will be the final transfer function if we consider the load torque is proportional to speeds. This is one special case. Another case, شباب, if we consider the inductance equals 0, someone can say we need now to consider the machine working at steady state without any changing in L. So if you would like to apply L equals 0, this means that electrical time constant TA equals L over R will be 0. So substitute in the equation just by tau A equals 0, you will get the mathematical model or the transfer function at that condition. Another case, for instance, if you can see that the friction torque is small and you can neglect the friction torque for the approximation to simplify your model, it's possible as well. So if we consider B equals 0, just substitute in the equation, okay, by the same way B equals 0, and you can get the transfer function easily. So all of these are considered as special cases from the main case we have. Another special case here, Shabab, if the supply is shut down, if you disconnected the supply, this means that the current will decay to 0. So the final value of current will be 0. In this case, you can substitute in the dynamic equation T electric equals K multiplied by IA, which is 0 now, equals JD omega by dt plus B omega. From here, شباب, you can say that B omega equals minus JD omega by dt. And if you convert to Laplace domain, considering the initial condition, you know this is the Laplace transform when we consider the derivative and get the initial condition. So the relation will be B omega of S minus J S omega of S minus omega naught, where omega naught is the initial speed, which means the speed before disconnecting supply. Now, this will be your relation, omega of S. And if you would like to get the time domain, you need to make inverse Laplace transform to get the time domain relation of omega of t. As you can see, finally it will be omega naught e to power minus t over tau mechanical. طبعا t is the time and tau mechanical is the mechanical time constant. So the relation will be like that, شباب. Okay. So all of these, شباب, are special cases for the main function we make. طبعا شباب, if you have your own model, which is here, you can define all of other cases by just inserting these parameters from M file, for instance. So you will have a block diagram for all of the motor, and you can define all of parameters from M file. Just if you would like to study one special case, add the value of this case by 0, for instance. If you have 0 inductance, so TA will be 0, substitute at TA equals 0 and see the response. What is the response? What do you mean by response? Apply certain voltage and observe the value of speed. Apply certain load torque at certain voltage and observe the value of speed, and so on. Okay, so this is the meaning of the response of machine. Now we need from your side to make an activity. This is activity number 6, شباب, as I believe, صح? We had previously activity number 5, which was related to pulse width modulation converters, and the deadline is the midterm, I believe. مظبوط شباب?
Yes, to it, yeah.
Right. So here we have another activity for DC machine. We have 5 horsepower, 220 volts separately excited DC motor. RA is given, KM is given, RF is given, LF is given. The armature winding inductance is negligible. So here you have LA equals 0, which means electrical time constant equals 0. The torque required by the load is proportional to the speed. We had already this special case. The combined constant of the motor, armature, and load are J equal 3. So this is the total inertia, and this is the total friction. Let the field current be maintained constant at 1 ampere. This is now the value of the field current. What is needed here, شباب, in the activity? Develop the transfer function omega of S over V of S and the corresponding block diagram. Compute the steady state speed corresponding to a step change of Vt equals 220 volt. How long does the motor take to reach to 0.95 of the steady state speed? At part number B. Determine the value of total effective viscous damping coefficient of the motor load configuration. Okay, شباب. This is the activity. We can make the activity. The next one will be March mid, so we can make it 10 days after that. So we can make it at March 25th, for instance. Okay, شباب. So I will pronounce the day of the due date for the activity number 6 as an assignment on Blackboard, inshallah. Do you agree يا شباب with this day or you have conflict with other exams or anything? We can postpone, no problem. Hmm. Is it okay for you?
For me, lecture, I have exam on the same day of the due date.
25. طيب يعني let make it يا شباب by March end of March, okay?
Okay. That's fine.
ماشي. Okay, so by the end of March now, يعني you will have 2 weeks after the midterm to submit this activity. طيب. Any question يا شباب? Everything is clear today? طيب. اوكي، يعطيكم العافية يا شباب. نراكم الكلاس القادم ان شاء الله على خير. السلام عليكم ورحمة الله وبركاته.
دكتور